Okay, so you have a quiz to work on. Quiz 2 is on Canvas. It's due this Monday. Let's see, I also want to write next to it, exam 2 will be next week. Okay. Both are on sections 2.6 to 3.5. Double check. 2.7 to 3.5. And the test will be on WebAssign. Okay, homework. You have some homework due this weekend, but of course, if you ever need more time on homework, just ask for an extension or send an email. Okay, so this would be sections 3.3, 3.4, 3.5. That's everything so far. Just a reminder that the final exam will be mostly like exam 3, not very cumulative, just focusing on the last few sections. And we will do homework for chapter 5, but I won't test on chapter 5. Okay. We've made it to chapter 4, and we're going to do notes for 4.1. Extreme values. Like maximum. So we're going to let f be a function. So this is definition. All right. Here we go. With domain capital D. Let C be some number in D. So some value in the domain of F. So before we go into different parts of the definition, I want to draw some examples. The first example looks like this. Graph with your function f is going to go up and then down and down and down. So this we call a local max. Same for this spot here and this spot here. Let's put that over. Okay, from those maxes, those local maxes, this is an absolute max. Also a local max. And in this example, there is no local min. Oh no, there are local mins, but there's no absolute min. Write that first and then label the other guys. Okay, right there and right there, those are called local mins. So it's local min. That one too. Okay, try that again and move on. Next example. The function looks like this. Start from A to B. The function is kind of here, dips below, and comes back up. Here, down. This is actually, this we're going to have jump up a little higher and then over like this. We'll talk about that other situation soon, but we'll come up. That's going to be a local max right there. This is an absolute min. And then this is going to be an absolute max, but not a local max. We'll talk about that today. See, so we can have an absolute max like this. We can have our absolute min. Anything else, local max is cool. All right, so now we're going to go into all the different parts. Being an absolute max, an absolute min, or a local max and a local min. We've got an absolute max at x equals c. that over. If f of c is greater than or equal to f of x for all x in the domain of f. Okay, so here's a symbol that you may have seen before or you will start using soon. It means element of. So x is an element of the domain of D. I mean, of the domain of F. Number 2, F has an absolute min at x equals C if this time we'll have f of c less than or equal to f of x for all x in the domain. All right, number 2, absolute min at x equals c if f of c is less than or equal to f of x. For all x in the domain. So this could also mean exists in, so all x that exists in the domain. That's another way to say it. Number 3. This time we have a local min. At x equals c. For all x in an open interval around c. Last one. Number 4. We have a local max. Okay. Keep some color. And do local min. I didn't. Local max. I think I left a little bit out. We need a local min at x equals c if, let's back up. Let's just redo number 3. Redo this one. So we're missing a piece in the middle. Local. Going back to this again. It's similar. We have if f of c is less than or equal to f of x for all x in an open interval around c. So for x values that are near c. Let's not put the word all, it's a little confusing. For x values in there we go. Let's see, we did absolute max, we did absolute min, that was our local max, our local min, we need local max. And I think we're ready. So, number 4. Let's go back to this one. X equals c. If f of c is greater than or equal to f of x for x values in an open interval around c. Okay, there we go for our definitions. I think we get to do examples next, but let me check out that I got this all down. Local max looks good. Local min we fixed. Oh, I want to talk about open and closed intervals, and I do have part 5. So, talking about endpoints on a closed interval. Before we go to that, though, so just want to remind that the open interval has those parentheses or non-included endpoints, and a closed interval does include the endpoints. So something like this is open. It's an open interval. brackets, square brackets, around a comma b. This is a closed interval. We want to talk about something like that. Okay, so let's just, I could start part 5, but I think I have an okay way of explaining it at the end. So let's go. Talk about a closed interval. The endpoints could be absolute maxes or mins, but they cannot be local maxes or local mins. Okay, can't be an endpoint that's a local max or local min. Okay, so I think I can explain it better if I draw a picture, but first we're going to just try to write it out. So it's the problem of needing to create an open interval around the endpoint, but you can't do that because that end is included in the interval closes off right there. So I put, you can't create an open interval around the endpoint. Then I'll try to talk through that with a drawing, with a sketch. Okay, so I've got, you can't create an open interval around an endpoint. So the domain of f is going to go from A to B. And let's go here a little bit and then up. Is that what I want to do? So just be more interesting. So this is fine. This would be an absolute min, and that would be an absolute max. But neither of them can be a local, this cannot be a local min, and that cannot be a local max. Let's focus on this one. Okay, so we said A can be a absolute min. But if we want to create an open interval around A, like this, the domain is cut off here. So this set becomes this partially closed interval. And so we can't use that part. We can't call this a local min because the definition needs that open interval around that value, which we can't create. think that's good enough. Let's try an example. So this is a function I made up. The graph looks like it has two pieces to it. There's a vertical asymptote up here. And the function comes from the x-axis up and over. Okay, other side, we're going to go up to a peak and then drop down and to the side. So over here will be the absolute max, and this graph has no absolute min. It's that part right there. Put that on the side. No absolute min. That would be a local max, and I think that's all we have. Cool. Next one. It's another function that I just kind of drew a sketch, so we'll start the new board. Okay, our graph looks like it's not going to cross the x-axis. Like that. And over. We're going to start on this side right here, and then jump here and slowly squiggle back up. Nope, we're going to come back down. We're going to go up one last time and drop it down. Okay. I think that's everything. Oh, I also kind of want to label, I was going to label that the values that correspond, the value that corresponds to having that max, but just labeling the max and min themselves, that's good enough. Okay, absolute max. Over here, which is also a local max, so put that here. This is an absolute min, and right here we also have an absolute min. It doesn't go past, it just stops right there. Then that's a local max, local max, local max. And then local min, another local min. Cool. We have some time. So let's see if we can do more. Past this part. Any questions though? I am kind of feeling like we don't need another example, but I can do one. Okay, so the next idea is to draw a bunch of continuous functions on closed intervals and then talk about the extreme value theorem. Okay, we're going to draw some continuous functions on a closed interval. First one. We've got the interval from A to B. And a function f. F is just going to go straight across like this. Start here. It's a constant function. It's supposed to be flat. And every single value is an absolute max and absolute min. Another one, we're going to draw, let's see. Number 2. This is my x, y. This function is going to go from A to B, closed interval, A to B. We're going to have a curve and peak up and over. Okay, labeled a few parts, absolute min and absolute max. And then we're going to talk about the extreme value theorem. I think that's it for today. So what happens is we'll read through it first, maybe try using this picture, and then get it on the board. So f of x is a continuous function. We've got one right here. It's continuous. I can draw my function without ever lifting my pen from the board. So I can start here and no discontinuities, no need to lift the pen. Okay. It will have an absolute max at f of c and an absolute max, it will have an absolute max and an absolute min for some value somewhere on that interval. So somewhere on that closed interval, you can find an absolute max and absolute min. Space. So f of x is a continuous function on the closed interval from a to b. Then f of x will have an absolute max I'm just going to call it f. F will have absolute max. At a c. At f of c. We'll talk about that at the end. Okay, absolute max. And we're going to also have an absolute min. Let's see, we're going to call it f of d. Where c and d exist in that closed interval that goes from a to b. Okay, so c is an element of that closed interval. D is also an element of the closed interval. I think we're going to draw another picture. Let's just put up part of the sine function. So we'll go from the origin, go through one cycle, have an absolute max and min. This is our continuous function. We're going from A to B. A is equal to 0. And B is going to be 2 pi. This right there, this right here is a absolute max. This will be an absolute min. And for that part here, for the part that we just wrote down, the absolute min occurs at f of c. So this would be c. And -1 is equal to f of c. We had the absolute max. Let's see, I think it just erased. Sorry, that was for the max. Oof. So this was absolute min, and then the min for d. So this is d. And the max was at f of c. So this is f of c equal to 1. And that number there, x equal to c, gives f of c. Okay, where are we? Sorry. I think that's going to be good for today. So we'll come back next time and keep working on this section. And I will be in office hour if you have any questions. So